So, welcome to this second week of online lectures. Last week, Nils gave you an overview of the acoustic part, introducing you to acoustic fine elements. This week, we're going to continue with the fun stuff, and we're going to have the first encounter with acoustic mechanical coupling. So, we will formulate basic coupling mechanisms, looking at a very simple system in order to illustrate how this coupling actually takes place. Then we will go on sort of elaborating or coming from this very simple example into the fine element formulation that you will use in your code. In that, we will have to deal with what we call the coupling matrix, and also we will today introduce the absorbing boundary matrix on our acoustic domain. So, why do we study acoustic mechanical coupling? Well, actually, if we have something vibrating, then it will emit acoustic energy. And that, of course, sometimes can be annoying in the form of noise. That's often the case, and that's interesting in itself. Sometimes, of course, it's something we want. The most basic example is a loudspeaker. We know that when the diaphragm of a loudspeaker moves back and forth, it generates an acoustic pressure that we then hear as sound. Another example that we see here on this slide is the violin. And here we actually have a structure that resembles the plate-like structures that we have been looking at in this course. So the interesting thing about plate-like structures is that they are very efficient in radiating acoustic energy. And that's what's used in, for instance, a violin or a cello or whatever we see in this picture. When the cabinet vibrates, it emits the acoustic energy that we then hear as the violin sound. But it's actually not the only interesting thing that we have the radiating acoustic sound or noise from vibrating structures. The opposite also takes place. So every time we have an acoustic signal, a pressure variation in air or in another fluid medium in water, for instance, it will actually, if we have a structure embedded in this acoustic medium, the fluctuating air pressure or water pressure will actually act as a load on our structure and thereby generate vibrations. This effect in some cases might be very small and often neglected, but in other cases it's actually very important and will affect the behavior of the structure. And it turns out that if our structures are very small, for instance, if we have very thin and light structures, such as very thin plates made from a very flexible material, this effect of the acoustic air pressure, the fluctuations onto the vibrations of the structure actually becomes very important. And this coupling, this effect can actually change the structural behavior also, not only quantitatively, but also qualitatively. Here to the left, I've show you one example of a case where it's actually very important to take into account the effect of the air pressure onto the structural vibrations. This is the case of a hearing instrument, and what is actually quite amazing here is that inside the hearing instrument we have the receiver that we see here, and it actually generates very, very high sound, up to 135 dBs. And at the same time, we have very short distances here. We have, a distance here, you can see 2 to 3 millimeters between the receiver, which is actually another word for a loudspeaker in a hearing instrument, and a microphone. So we only have 2 to 3 millimeters of distance between the receiver and the microphone. We have 135 dB of generated sound. And furthermore, we have shell structure here, which is just plate structure on the outside. It's very thin and very flexible. So we will have a significant amount of vibrations generated by the loudspeaker or the receiver. And in turn, these vibrations are actually transformed back into an input signal to the microphone, which is a bad effect. So we have what we call the negative feedback loop. So in many cases, this effect is really interesting, and the coupling between the vibrations and the acoustic pressure really becomes important. So we're not going to start directly with the finite element theory. That would be too complex, and I think it makes sense to start with a really, really simple example. The most simple example that explains the coupling between mechanical vibrations and acoustics. So what we're going to look at here is actually the most simple mechanical structure you can think of. It's a linear spring stiffness K. It's a simple mass, M. So it's a mass spring model, a mechanical model. So it's a discrete mechanical model. And we then couple that to a 1D acoustic domain. So what you might think of, if you think of the mass here as a disk, a circular disk, and then you think of this part here as a circular tube, then you might think of the whole system as a mass spring system where the mass is actually embedded into a tube where you have air inside. So this is the basic system that we're going to look at. So the basic question that we will try to explain or try to answer in this study is to see what effect does this acoustic domain that we have inside this channel or this tube, what effect does that have on the behavior? We pretty much know what the effect or what the behavior of a mass spring system is. We have all the formulas ready. It's very easy to analyze analytically. We have the natural frequencies and with damping. We know all these kind of things for a simple mass spring system. So now we want to study what is the effect of this 1D acoustic domain being attached to the mass. As I said, it's a little bit funny. Well, it's a very simple structure, simple system, but it's a little bit funny because we have a discrete mechanical model, which is modeled by a ordinary differential equation, but we actually have a continuous acoustic domain, thereby it's modeled by a partial differential equation. So we have a set of one ordinary and one partial differential equation. But still, we are going to be able to create an analytical solution so that we can actually have a very, very good idea of how this coupling affects the system, or how this acoustic domain actually affects the behavior of the mass spring model. So let's start with the behavior inside the acoustic tube or acoustic channel. This is going to be based on what Niels told you last week. He already showed you that when you are modeling acoustic wave propagation, acoustic pressure fluctuations, then we end up with what we call we end up with the wave equation in general. And in this case, if we just go back, well, it's a 1D domain, right? We're only going to have things going on in the x direction. Y and Z directions are gone here, so we only have a 1D acoustic model. And that means that our wave equation reduces to this 1D wave equation. So we have the pressure fluctuations. So we have the second order time derivative of the pressure minus the wave speed squared multiplied by the second order derivative of the pressure with respect to the actual coordinate equal to 0. So that's the basic 1D version of the wave equation. So what we're going to be, of course, specifically interested in throughout the course actually is time harmonic motion, right? So we have a well-defined frequency of the motion. So we introduce the frequency omega. And when we do that, then we can transform our 1D wave equation into the corresponding time harmonic wave equation, also known as the Helmholtz equation. So this gives us the basic equation that we want to solve. And actually, it's also, this is a very well-known differential equation, and we have the solution, the general solution for this differential equation. So we can write up the solution for the pressure inside the acoustic channel directly. So this is given by the bottom formula here. And as we see here, we have the frequency, capital omega, so the frequency of the signal or the wave. We have the wave speed inside the wave speed of air, we have the actual position x, and then we have two unknown constants, a and b. So of course, as always, when we solve differential equations, get some coefficients, unknown constants, then we have to solve them by using the boundary conditions. So a, b, found through boundary conditions. So let's see how we're going to determine a and b. All right, so to do that, well, then we actually go right ahead and study the coupling to the mechanical vibrations. So there will be two coupling conditions that we have to enforce, and the first coupling condition actually expresses how the mechanical vibrations affect the acoustic medium. And we have here boxed expression that will actually state how this should be interpreted. So what we state here is that the acoustic particles at the interface must follow the motion of the piston. So imagine your piston is moving back and forth. Then of course the acoustic particles right in front of the piston must move along with the piston, right? So how we express this is that the acceleration of the mass will be equal to the acceleration of the acoustic particles expressed as the velocity v differentiated with respect to time at the position of the mass. That means for x equal to 0. So x equal to 0 represents the position where the mass is located. So we will express that the acceleration of the mass equals the acceleration of the fluid particles. So this makes sense. And we will use this short notation, v naught dot, to express the velocity differentiated with respect to time at the position of the mass. Right. So this gives us a connection between the acceleration and the velocity of the fluid particles. However, as we see here, in our acoustic equation, we don't have the velocity present. But as Niels also showed you last week, in the fundamental acoustic theory, there is actually, and setting up the differential equation, the wave equation, actually involves considering this. So there is a direct connection between pressure and velocities, and this is expressed here in terms of the momentum conservation. So the momentum conservation generally expresses a connection between the acceleration of the particles and the pressure gradient. So this is, of course, something we can use in order to express the coupling condition that we have up here in terms of the pressure gradient, so that we can relate the acceleration of the mass to the pressure gradient in the acoustic medium. But first, let's see how this equation down here, that's the general 3D equation. Now first, we express that in a 1D setting, which we have here. So we just take the x component of this equation. And then we use that to express, we get the pressure gradient at the interface equal to then minus rho a, which we have here, rho a, and the velocity at the interface. So this is what we express here using this equation, evaluated at the interface. And then we see, okay, our v naught dot is actually the one that we had up here in our coupling condition. So that means that we can now express our pressure gradient at the interface by our acceleration of our mass, and then we have the density of the fluid and a minus sign in order to express the full connection. Now again, we will be interested in time harmonic motion, so that means that we can directly replace the acceleration of the mass by our omega squared times our displacement here, and then getting rid of the minus. So finally, we have the whole thing. We have the first coupling condition that we need, and we need that to find, the first step is to find the two constants in our differential equation. And our coupling condition gives us a condition that we can use to find one of the constants. And this coupling condition is the one that we have expressed here. Now, of course, we're going to need two conditions in order to solve for the two unknown constants that we had in the solution for the acoustic differential equation. And in order to find the second one, we need to somehow specify what is going on in the end of the channel. So this is for x equal to L. What is going on down here? And there are several options, of course. We could have an open channel, but we could also have a closed channel where we sort of put in a plug, and then we will have a closed cavity as our acoustic medium. So a completely closed cylinder with our air. So let's first take that as an example. So we will study the solution valid for a closed cavity. Now we know for a closed wall or a closed cavity, we have a hot wall boundary condition at the end. And as Niels showed you last time, a hot wall boundary condition means that our pressure gradient at that position will be equal to 0. So this will be our second condition. Now, in order for us to be able to use that in order to define our two constants A and B, let's write up the general solution and then differentiate that, because we're going to use the gradient, the conditions on the gradient. So we need to create an expression for the gradient of our general solution. So here we have taken the bottom equation here. We have taken our general solution expression and differentiated with respect to x. Next step is that we then evaluate this gradient at the right boundary at x equal to L. Insert x equal to L here and here. And then we set this expression to 0 because we have the hot wall boundary condition at the end. So this directly gives us the first connection between the two constants in the acoustic equation A and B. And now we then go back to the coupling condition that stated the difference or the connection between the pressure gradient at the interface or the at x equal to 0 and the acceleration or the displacement of the mass. And inserting the conditions in that, we get the second equation or second condition that tells us that the pressure gradient should be equal to omega divided by the speed of sound multiplied by this coefficient b. And we can see here that has been obtained by inserting x equal to 0. Then we get a 1 here. And inserting x equal to 0 here, we get a 0 here. And that means that totally we get omega Ca multiplied by b on the right hand side. That's what we find here. That was for the general solution, and then we, as I said, we set that equal to the acceleration here on the right hand side, and finally we arrive at the condition for the second coefficient or second constant b directly in terms of our our displacement, our frequency, our speed of sound, and our density of the acoustic medium. That we can in turn use to find the expression for A up here. And then, voila, we have the complete final expression for the pressure distribution in the cavity. So remember, two constants found, one of them by a coupling condition to the mass at the left end, the second found from the conditions that we had a closed cavity at the right end. Now here we can just simply write up our pressure for any x, for any position in the tube or in the channel. We can note a few things. We can see that the pressure that we get inside the acoustic channel is directly proportional to the vibration amplitude of the mass. So the more the mass vibrates, the larger the pressure in the channel. This is perhaps not surprising. We can also see another thing that's a little bit interesting, that the pressure is directly proportional both to the density of the acoustic medium and also to the speed of sound in the acoustic medium. So in other words, how much the vibrations actually affect the acoustic medium is actually dependent on which type of acoustic medium we have. So if we have, for instance, a water, which is denser and has a higher speed of sound, then we have a higher effect. Whereas if we have air, for instance, then we have a relatively small effect on the acoustic, of the vibrations on the acoustics. Third thing that we should note here is that we have this term in the denominator here. And that means that this term, of course, can go to zero. And that will happen if we have what we call an acoustic resonance. So we could have vibrations going on at a frequency that will lead to acoustic resonances inside the chamber. So we already last week saw about acoustic resonances in a room or in a confined box. And here, of course, the same thing can happen when we have this tube that is closed at both. Well, it's closed at the right end, and then it's attached to the mass at the left end. So we can have the acoustic resonances. Yeah, and just showing further this thing about the acoustic pressure and the effect of resonance, and also the effect of frequency. We here show the pressure distribution inside just a sample acoustic chamber or acoustic channel for the 3 different frequencies. So this product Ka times L is actually equal to, not that one. Let me erase that. Omega divided by Ca multiplied by, not X, but L is the same as Ka. So Ka is the wave number, Ka times L. So we see here, if we have Ka multiplied by L equal to 3, we have relatively high pressure. And why is that? Well, it's because this number is quite close to pi, which would actually correspond to this term going to 0. So this is actually close to a frequency of an acoustic resonance, right? The amplitude is more moderate if we come away from resonance, as we see for the other frequencies. But here we then see the effect of the high-low frequencies in terms of the variation of the pressure distribution inside the channel. Okay, but then of course, this is just one side of the story, because we can of course also consider the piston motion. And we need to consider the piston motion. So we saw now how is the effect of the vibrations onto the acoustic behavior inside the channel. Now we want to see what is the effect on the piston motion. And here we have a much more simple system, right? It's an ordinary differential equation, and this is a well-known equation for a mass spring system. So we see here mass times acceleration, stiffness times displacement, and then we have the external force onto our mass. So what is the external force here? Well, that of course comes from the pressure signal, right? Or from the acoustic pressure. So this is going to be what we can call our second coupling condition, right? So we have the pressure at the interface of our mass expressed here, the pressure for x equal to 0 as a function of time, and then we multiply it onto the cross-sectional property or the cross-sectional area of the piston. So inserting, and then we do our normal trick that we usually do when we consider a mass spring system. We divide by the mass and introduce the natural frequency of the mass spring model. And then on the right hand side we then get the following expression for the load onto our mass. Again, then in the final equation we see here, when we look at time harmonic motion of the frequency capital omega here, then we get that equation in order to solve for the vibration amplitude omega. So this equation basically describes how our external load in terms of the acoustic pressure affects our mass spring model. Now you can see here on the right hand side, here we have the pressure at the interface, but we have the expression for the pressure that we derived in the previous slides So we can simply insert on the right hand side the expression that we have already derived for the pressure at the interface. So now we can see here we also have the displacement. We saw before that the pressure was directly proportional to the displacement of the mass spring or the mass. So we actually in our system then get a system where we have our displacement of the mass here, but also the displacement of the mass over here. So that means, of course, we can collect all these expressions, and then we get finally a expression that determines our motion of our mass as this final equation that we can see here. So this actually expresses what we were interested in the first run. So we were interested in finding out, using this simple example, how does the presence of an acoustic medium, how does that actually affect the vibration of our mass spring model? So this last term here only comes about, because we have the acoustic channel. If we hadn't had that, then we would have simply a simple mass spring system where we know that the resonance frequencies are simply given by this square root of k over m, and then here expressed in the dimensionless frequency omega tilde would simply be 1. Now, if we go back and see on this expression again, in the final expression, we can see that there are a lot of parameters entering. We have the cross-sectional area, capital A, we have the speed of sound, we have the density of the acoustic medium, we have the spring stiffness, capital K. So it should be possible to actually define a fewer set of parameters that actually characterize the effect of this, the effect of the acoustic medium onto the mass spring model. And this we can actually do by introducing two new parameters, two new non-dimensional parameters. So the most interesting of these is what we can call the coupling strength, and we will call it delta. So the coupling strength actually combines a number of the parameters in the system. So we have here in the denominator, we have the mass density and the speed of sound of air. And in the bottom here, we have parameters from the mass spring system. So the mass, the stiffness coefficient, and the cross-sectional area of the mass, the piston. This is not exactly enough to have one non-dimensional parameter. We need a second one. And we can see a relevant non-dimensional parameter in this case is what we call gamma here. So gamma can be expressed in terms of the parameters as this, but we can also identify it actually as the ratio between the natural frequency of the mass spring model, omega, and the fundamental natural frequency of the acoustic channel, which is stated over here, omega A. So in other words, we have the two parameters, one representing how much does the acoustic medium and the vibrations, how much do they couple, and the other one expresses how far are the fundamental frequencies, the natural frequencies of the two systems, how close are they to each other. And introducing these two parameters, we can see that we can actually express our equation for the mass now like this. Okay, of course we can actually see this is an eigenvalue problem, right? So we can solve this for the new natural frequencies of our system, because now we have a combined system, so we will have a new set of natural frequencies for the combined system. So we want to solve this for our non-dimensional natural frequency omega tilde. But we can see here this is quite a nasty system because it's nonlinear. We have a tangent function in the denominator, and we cannot just readily solve that for all cases. However, for certain cases, if we have a very short cavity, and what do we mean by short cavity? We mean that what that implies is that the natural frequencies in the acoustic channel are very high. So if that's the case, then we also have that the gamma parameter defined on this page will be very small. So if gamma is very small, then we can apply this approximation of the tangent function, and then we can actually turn our system into something that we can solve, because then the natural frequencies are found from this system, which we can then reduce to finding the non-dimensional natural frequencies using this very, very simple formula. So what we can see here is that if we didn't have any acoustic medium, well, then the natural frequencies expressed in a non-dimensional form would just be equal to 1. Well, that's what we knew. But then when we have an acoustic chamber or an acoustic channel attached to the mass, then the new natural frequencies will be modified. So we see here that it's simply expressed by our delta parameter and our gamma parameter, and then a factor of pi here in the denominator. So what we can also see here are that if we have a very short channel or a short cavity, air cavity, then we will always have higher natural frequencies than we would have had if we did not have the channel present, if we just had the mass spring system. This number will always be larger than 1 if we have an acoustic medium present. And we can also see that the higher the coupling strength, the larger the change of the natural frequencies will be. Okay, so we can just exemplify how this actually how this manifests itself into a frequency response. So this is not solving the eigenvalue problem, this is solving a forced vibration problem. So here we just assume that we have a system, it could look like this. So we have our spring, we have our mass, we have our acoustic medium here, which is closed. And then we have an external force acting on our structure as well. All right. So now we can then see what actually happens in this in the limit cases when we have either strong coupling or weak coupling, exemplified or characterized by this delta parameter. And also for different values of the gamma parameter that expressed how much are the frequencies of the natural frequency of the mass spring model and the natural frequencies inside the acoustic chamber, how well are they separated. So in this case, we see here the frequency response for this system when the structural and acoustic frequencies are well separated, and that means that the gamma is not very close to 1. So here we have that the natural frequency of the mass spring system is equal to 1, and the acoustic natural frequency, the first of the acoustic natural frequencies, are equal to pi, or is equal to pi. Now, if we have weak coupling, then we can see that the new natural frequencies, remember now we have the coupled system, then we have combined natural frequencies, but the new combined natural frequencies of the combined coupled system will still have these natural frequencies close to 1 and close to pi. So we will not see any change really overall in our response. And change in that way that we would have had the same if we would just have considered the two systems separately. Now here we still have the acoustic and the structural frequencies for the separate cases. Well, they're well separated. We still have omega equal to 1. The acoustic natural frequency equal to pi. But now we have a strong coupling, right? So our delta is much larger than before. And now we can see that it actually modifies. Our combined system now actually behaves in a different way than if we would have just had the two systems separately. So our first natural frequency of the combined system would be 1.3, and the second one 3.8. So quite different from the uncoupled systems. Now we can go on, and here we now see the case where the structural and acoustic frequencies actually are close. They're actually pretty close to coinciding. We have omega, but also the first acoustic resonance being equal to 1 or close to 1. But we have weak coupling. So we can see some funny things happening down here because we have two resonances that are close So we have some interaction going on between the two natural frequencies. So we got a rather funny behavior in the frequency response near this natural frequency. The high order acoustic resonances still appear where we expect them to be. So this is at 2, 3, 4, and 5. Now finally, we can have the case where we both have that the acoustic and natural frequencies are close to each other, and then we have strong coupling. And then we see down here, funny things are going on. We have the first frequency of the combined system being 0.6, even though for the uncoupled system, the net resonance frequencies are close to 1. And then we have the second resonance around 1.4. So when we have strong coupling and closely residing frequencies, then things become really complex and difficult to interpret. Now, the second thing that we need to do here is to take the other basic boundary condition into account. So before we saw the effect of having a closed end of our acoustic domain, and now we will see what happens if we have an open end, right? So we simply have assume that our channel or our acoustic domain is open at the end here. So now let's see how that changes our system behavior. Well, we still have the 1D wave equation. We also have the same general form of the solution as we saw before. But what we will use this time is that we can actually write this general solution in an alternative way using complex notation. So writing it like this, I should mention here that the two constants C and D, even though I use the same symbols, they will be different. It's not the same constants, but I mean, we will solve for the constants, so it doesn't really matter. But in principle, the symbols should also be different. So the benefit or the good thing about writing the solution in the second way here is that we can actually interpret this solution form as the sum of a wave traveling in the positive and in the negative direction. So we will see now why that's beneficial. Because when we have this open acoustic domain, then we actually know that all waves that travel towards the right, they will just go on forever. It's radiation to infinity. They will not come back. They will not be reflected by the closed end or any other end. So we will have no waves in the acoustic domain traveling from right to left. And that means we can actually directly write up that the second part of the solution is 0, right? Because this represents the backward traveling waves, and this can simply not happen when we have nothing in the end to reflect the waves back. That means that we have very easily determined one of the constants, d equal to 0, and we can write up the equation for the pressure fluctuations like this. And then we can simply redo the calculations for the boundary conditions where we have the coupling to the mass using the pressure gradient equal to the mass density times the acceleration of the mass, and using that in writing up the general form of the pressure gradient here, doing the coupling up here, then we can just simply insert and find the expression for the constant C as this, and write up the total pressure field inside the acoustic channel with the bottom formula. So it's expressed in terms of the complex, in the complex plane. So if we then see when we insert this new solution into our equation for the piston for the time harmonic motion, we get the second equation here on the slide. Moving around a bit, we can see that we actually can express our equation in this form here. And if we look a little bit on this equation, we can actually see that it resembles very much the single degree of freedom oscillator, mechanical oscillator when we have damping present, right? So the second term here, when we have the imaginary number, is really what we also see when we add a simple linear viscous damper to a mass spring model. And that means we can directly write up actually the equivalent damping factor when we have an open channel then we get the equivalent damping factor simply in terms of these parameters. And then we can see we can actually write them directly up in terms of our coupling strength parameter. So this is quite neat. So we can actually, just by knowing the coupling strength, we can actually predict how much do we have, how much is our resonance damped, right? So just going back, we can actually now, just to sum it up, we can see that the basic effect on the piston motion of having an acoustic medium, if the end is closed, then we would have a change of the natural frequencies. And how much they change, that depends on the various parameters. And it could be complicated if the frequencies are close and so forth, and we have strong coupling. On the other hand, if our channel is open, then the effect is a little bit more simple than we see here. Then it just acts as a damper, right? And we can actually directly predict how strong the damper is based on the parameters. So this was for the simple model. When we get to 2D plate with a 3D acoustic medium, then things are a little bit more complicated, but the basic effects are still there. So in order to get us going into the final element formulation that we need to implement in our code, let's just take a step further and look at the general acoustic mechanical coupling. So here we basically have an acoustic domain and a structural domain that is coincides, that touches in a part of the boundary signified by this domain here. Now, if we look at the acoustic domain, Niels showed you last week all the usual, well, the equations and the typical boundary conditions, right? So what we had here was the hot wall boundary condition, pressure release condition, and then the the absorbing boundary condition that we could also have on the acoustic domain. So now we just need to formulate what we have, how we can formulate our coupling boundary condition if we have a adjacent structural body, vibrating body. And we use the same approach as we did for the 1D model. We just use the more general equations. So we take a look again at the momentum conservation, but this time not reduced to a 1D equation, but simply the vector equation. So we see here how we can express our desired quantities. Now what we do with this equation is we simply multiply both sides of this equation with the normal, interface normal, the NA vector here. Simply multiply on both sides of the equation. And then we use the interface boundary condition, we use the coupling condition in saying that, okay, we know that the acceleration of the fluid particles are equal to the acceleration of the mass at that point, right? So now we have connected our interface coupling condition down here, expressed in the way that we want it to be expressed. Now we do one small trick here is that instead of having the normal, well, NA expresses, as shown in the drawing over here, NA expresses the normal vector going away from the acoustic domain. Now we replace on the right hand side with a normal vector going out from the structural domain instead, as seen on the right here, because then we separate on the left side everything that deals with the acoustic side, and on the right side we have everything that deals with the structural part. And then one step further will be to introduce time harmonic motion. We can replace the acceleration by minus omega squared times the displacement. And then we get the final equation in the bottom here. And that means we can actually complete now our full set of boundary conditions. Of course, you can think of other boundary conditions, but these would be the typical boundary conditions that we will deal with here. So now we just need to put that into a finite element framework. So we will do it. Well, Niels did it with most of these boundary conditions last week, but we will take the final two boundary conditions here and see what the finite element approximation or the finite element equations become for these two final boundary conditions. So as the starting point, we will take the weak formulation derived last week. After doing the integration by parts, we have this part here representing the or now let me just erase that. So not everything here. But this part represents the boundary term that comes from integration by parts. For the hard wall boundary conditions, this expression simply vanishes. And also for the pressure release, we implement our boundary conditions later. But for the two boundary contributions that we will look at now, which is in the case of an absorbing boundary condition and in the case of a coupling boundary, then we can simply express the value that we have obtained for this pressure gradient vector term here that we have on the two right-hand sides here, right? So instead of this, we insert directly into, for the absorbing boundary condition, we insert this expression, and for the coupling boundary, we insert this expression that we have just derived. So in the second step here, we retain this step here, it's the same as above, but here we can actually see that this is a general term for a vibrating elastic body. But if we have a plate, which we will look at in this course, we know that the normal vector away from the plate multiplied by the displacement vector would actually equal the vertical displacements of the plate. So this is specifically for plates that we can simplify this product. So now we get the final weak form here with the two boundary conditions, or the two boundary terms that do not vanish. Insert the finite element approximation. So here we have the finite element approximation for the acoustic domain. And here we simply use the finite element approximation for the plates, noting that we are only actually interested in the vertical displacement. We're not interested in the rotations, which are also present in the finite element formulation for the plates. So that's why we need only the first term here in the shape function, right? We don't need the second and the third one that corresponds to the rotations around the x and the y direction. So inserting all these finite element approximations into our equations, we get all of this, which we had last time, and then we get the two extra terms down here, where we see that the element summations here are only done on the relevant elements. That means that only summing up on the elements that belongs to the absorbing boundary, in this case, and only summing up over elements that actually belongs to the coupling interface between the acoustic medium and the plate in this case. Going on a bit further, we insert here, and we can now see that we are actually down to doing an element integration for the absorbing boundary that looks like this, and for the coupling to the plate that looks like this. So these are element integrations. So this leads us to two new element matrices that we're going to need. And as we see here, the absorbing boundary is going to give us a new absorbing boundary condition. New damping element matrix representing the absorbing boundary. So it's simply found there's a constant outside, 1 divided by the mass density and the speed of sound. And then we need to integrate the product between the shape function and the shape function transposed of the acoustic shape functions. That's what's going to give us our damping, local element damping matrix representing the absorbing boundary. In the second case, here down where we have here the coupling to the vibrating plate, we get a coupling matrix, coupling element matrix that we will call S. And that is found by integrating over the element our acoustic shape functions with the first component of our structural shape function. So this will, of course, represent the coupling that it includes both the acoustic part and the structural part. So this might look a little bit confusing, but putting everything together, assembling to the global equations, we see that if we separate all these terms that we have up here, this one we had last time, this one we had last time, and then the new two extra terms is a damping matrix coming from an absorbing boundary and a coupling term that couples to the vibrations of the plate, right? And here we have defined the global coupling matrix and the global acoustic damping matrix coming from an absorbing boundary. We might, of course, also have additional damping matrix in the acoustic domain, but this is the one that specifically comes from an absorbing boundary. So an open boundary where waves can sort of radiate out. Now we also need to look at the plate equation, and it's actually much simpler, because if we take a look back, we saw this equation in week 2. We see here that as a part of the plate equation, we have the pressure onto our plate. And this could, of course, be a general pressure load, as we also have treated in our code. But in this case, when we're dealing with the coupling, we can also use the acoustic load directly as the pressure here, so that the pressure on our system is simply the acoustic pressure. So much the same as when we looked at the simple 1D mass spring model. So looking at the finite element equations now, we see that on the right-hand side where we have the load, now instead of this being just a general pressure load, this is actually specifically the pressure of our acoustic medium that is close to, or that is actually residing on the plate. And we do the same as before. We insert the finite element approximations. And when we do that, well, this is following much the same lines as when we just did the finite element equations for the plate problem, except for this extra term on the right-hand side that now represents the acoustic pressure. So that means that also here we get a mixture of the structural shape functions and the acoustic shape functions. And here we have the pressure on our plate. So going further, reorganizing terms, we can see that we end up with a coupling term, and the interesting thing is here actually that we get the same coupling matrix as we did before, and that shouldn't be surprising actually, because when we have these two effects, there's the two sides of the same story. We have the effect from the pressure onto our vibrations, and we have the effect of the vibrations onto our pressure, both expressed with this coupling matrix that we call S. Well, the final plate equations then just gives us this extra term that we need to add to the finite element plate equations. And then, of course, we also may have damping in our plate in addition to this, of course. And this down here was our acoustic equation. So now we can see here that we actually end up with two coupled equations, because we have here the displacement, we have the pressure here, we have the pressure here, and we have the displacement here. So we can formulate that as a matrix or larger matrix system, where we have now a combined stiffness matrix here, where we have the structural stiffness matrix, we have the acoustic stiffness matrix, we have the coupling condition of the coupling matrix, then we have a damping term. So here we have added extra structural damping, because that we will have in the general case. Then we have a mass matrix that consists of a structural mass matrix, acoustic mass matrix, and also the coupling here. And then we, of course, might have some external loads on the system. We can see that actually if we now just interpret that as our new stiffness, damping, and mass matrices, a new load vector, and just introduce this short notation for just remembering that it is actually a combined matrix of both both structural and acoustic properties, then it actually looks completely like a normal structural problem, right? So we can use actually this equation, we can use all the tools that we have actually developed to analyze this. So that means we can do eigenvalue analysis, We can do a frequency response analysis with the direct solution. We can use modal superposition, and we can use modal reduction techniques. The only thing that we have to be careful about, and we will look more on that the coming weeks, is that, well, our equations here, or our matrices, our matrices will no longer be symmetric, right? Our stiffness matrix is no longer symmetric. Our mass matrix is no longer symmetric. So that will put some limitations in the tools that we can actually apply. And in some cases, we have to develop specialized tools due to this. It also means that the equation solving will be much more difficult. Also, simply because our system is larger in terms of number of degrees of freedom, but also because of this asymmetry that it will actually give some limitations. Okay, so now a few words about the element coupling matrix, because that's a part of the exercise you need to do today. So we will give some details here on how to actually do this. So going back a few slides, we found this expression for the coupling matrix. So as said, it involves the acoustic shape functions. It involves the first component of the structural shape functions. So looking a little bit on dimensions, we see that the shape function of the acoustic shape function is 8 times 1, and the dimension of this first component is 12 by 1. So the resulting element matrix will be of size 8 by 12. So in order to obtain this, we need to integrate over the interface where we have the coupling, right? So I'll try to make a drawing here. So if we have a plate here, and then we have the acoustic, so divided into elements, and then we have the acoustic median on top of the plate. So here we have a box of the acoustic. Also divided into elements. Well, this is going to be difficult, but let me just try. Well, so forth. Then if we look at this box down here, so here we have a box right on top, this box here right on top, box of air right on top of our plate element. When we formulate the coupling matrix here, we integrate on the interface between the plate element and this box. So that means that we're actually doing a 2D integration, right? And that also means that when we evaluate our shape functions for the acoustic medium, we need to evaluate it at the interface of the plate. So that means only a 2D surface. So what that implies when we do this integration, that all the degrees of freedom, if we go back to the box plot here, all the degrees of freedom of that box on the top here are actually not involved. It's only the degrees of freedom at the bottom where we have the interface to the plate that is involved. So that's why we make a bit of a simplification and see, okay, it's actually much more easy to just use the 2D pressure shape functions that are related to the bottom of the bottom interface, so that we simply don't need to take into account the set coordinate, because we are just evaluating at the lower boundary of the 3D acoustic domain. So we simply use the 2D pressure shape functions, and that means that when we do the element coupling matrix, it will be of a smaller size. But that also means that when we identify the degrees of freedom for the acoustic element, we need to concentrate on the lower 4 lower nodes of the acoustic box, because those are the ones that will be in contact with the plate element. So in order to create or compute the coupling matrix, we simply need to do this integration over the relevant shape functions. The 2D shape functions for the acoustic, which are given up here, and then again the first component of the structural shape function. So, summing up, the steps needed to assemble the global coupling matrix: we need to loop over all plate elements, and this is simply why, because we assume that when we have a plate and we are coupling to acoustics, then all plate elements will be covered by the acoustic domain. We will not have any cases, at least here now, where we just have some part of the plate being connected to acoustic medium. Everything will be connected. So when we then, next step is then to identify the relevant degrees of freedom for the plate element. That's exactly what we do also when we assemble the normal element or mass matrix. And then we need to identify the relevant degrees of freedom for the connected acoustic element. So the acoustic element is of course the bottom layer of acoustic elements. That's the only layer of acoustic elements that are connected to the plate. And then remember, we are only interested in the bottom degrees of freedom for those acoustic elements, not the top ones. And then we get the local stiffness or the local coupling matrix that couple these degrees of freedom. And then in order to build up the global coupling matrix, we simply do it in the same way as we do with global stiffness, global mass matrices. We assemble using the sparse technique that we have developed already. So this is one thing that we need to do today, assemble the coupling matrix. The second part is to assemble and implement the absorbing damping matrix. So that means if we have let me do the simple drawing again. Hope it becomes a little bit more clear this time. So we have the plate down here, and then on top of that we have an acoustic medium here. So remember, the coupling that we did before takes place on the surface of the plate, where the surface meets the bottom layer of acoustic elements. Now, if we have an absorbing boundary, of course, we will have that on the top layer of acoustic elements, right? And at least today, for the entire top layer. We will later on do implementations where we only have boundary absorbing damping for some parts of the top. But now the absorbing layer will be the whole top here, so that represents an open cavity. Now, if we look back in what the element damping matrix was that represented this absorbing damping matrix, then it took this form. So the shape functions are 8 by 1. That means that our resulting matrix will be 8 by 8. But again, we can actually do this simplification, because when we look now, remember, only the top layer of acoustic elements, but the absorbing surface is actually on the top of that top layer, right? So this is a surface integral over the top surface. That means that we can again use the 2D shape functions and then do a integral over just this top surface here. So that's what we do here. So that means that in the final part, now having the drawing again here, so we are on the top surface where we have the absorbing boundary condition. That means that we do this final integration in order to get our local damping matrix. And then, this was expressed with the 3D shape function here, then expressed with the 2D shape functions. Sorry, that's the final one here. So we do the integration on the 2D shape functions and then get with the local damping matrix for the absorbing boundary condition as this. Of course, we can modify this if we were to have damping or absorbing boundary conditions, for instance, on the side. That would be a possible that we would have a open hole in the box on the side, or we would only have maybe a part of the top being absorbing boundary conditions. We can analyze funny effects there that we can relatively easily modify our scheme afterwards to take into account that we don't have the whole top surface as an absorbing boundary. Okay, so we're almost done here. So let me just have a few words on the exercises. So actually looking at it a little bit, the first 2 exercises today are purely implementation exercises, so they should not be reported. And it's just, the first one is the coupling matrix, second one, absorbing boundary matrix, as we just showed. Those are the 2 first exercises. And then in the third exercise, we actually do some analysis. Okay, so there's a new handout script that is available on Learn, and let's just run through to see what that contains. So we have a script that is just used to start out and to find out what we need to implement. So, well, when everything works, when you have implemented the coupling matrix, then you can use this in order to compute eigenvalues as it is now, and then we will use next time. Sorry. Okay, so let's go down again. Yeah, then there will be some new routines for the find element part. There will be something called assembly coupled, and this is actually the part that you will start working on today, because this will assemble the coupled system. So it will assemble a 3D acoustic system. So it's actually a direct copy from Assemble Acoustics that you had last time. We have copied it directly into the assembly coupled. So it both contains a 3D acoustic and then a 2D plate. So simple couple copied from existing code. And then what needs to be done here is to assemble the coupling matrix in this routine assembly coupled and implement the absorbing matrix assembly. Right. So these are the things you should focus on to start with today. So these are the two first routines. This one, the script or the model builder, and then the one file where you do the modifications. Then there are some new element matrix, element integrations that needs to be done. So they're called by the previous function. The acoustic boundary condition, element integration that you shouldn't, it's not for you. This has already been done. And then there's the final script, and I will get back to that one. So in the controller, one thing you will need to do is you will need to add a new element, study element type, which until now could be Mendlin or acoustic, but now it also needs to be able to be coupled so that it calls the assembly coupled routine. Okay, so look at that, and hopefully it makes sense. Okay, let's go back. As said, the first exercise, implementation exercise only, implement the coupling matrix, this S matrix. Second part, implement absorbing boundary conditions. So that means a C matrix for the acoustic part. Okay, and so exercise 8.3 is actually the one that should be reported, and that is running a benchmark example. So that means we know now you need to both implement the coupling matrix, you need to implement the acoustic absorbing conditions, and things could go wrong, of course, in this case. And you should also remember that you should still be able to have two materials. You should still be able to have damping, proportional damping, stuff like this in your code. So in order to make sure that everything is working, we have provided now a benchmark example. So that is also in the uploaded files for today. So the idea is that you have this file. Now let me go back again. Let's see here. That one, the run benchmark handout. So that means that if your code is working and everything has been implemented as they should, if you run this, then it will produce a number of data files for these systems. That is described here in the benchmark. So there are 3 different cases. There is a non-proportional damp plate with 2 materials, so no acoustics. There's an undamped 2-material plate coupled to a closed acoustic cavity, and 3 non-proportional damped 2-material plate coupled to an open acoustic cavity. So these 3 cases actually tests quite broadly all cases that we can think of. That means that if you run this script in your code, if things are implemented correctly, you will get some output files. Then you can then compare to output files that have also been uploaded in this today, and you should of course get a match with these files. So then these are in terms of frequency responses, and you can compare these frequency responses to your own output from your code, and hopefully they will match. And then finally, you just should comment a little bit on the observed system behavior as a final part of this exercise. Okay, so final, not obligatory part is to do a COMSOL. Try to use COMSOL to do the same stuff. Now you cannot access the data bar, so you can use ThinLink if you know how to do that. If you know how to do ThinLink, then it still should be possible. But of course, it's not an obligatory exercise. It could still be fun though. So if you have the possibility, I would recommend that you do it. Okay, so this ends the lecture. Yeah, like this. And we will start the session here on MS Teams, I think around, in 15 minutes or so. So hope to see you then.